right, so again, we're into our last part of collisions, and what we're looking at is the conservation of momentum, this time in two dimensions. So we're not going to talk about, I don't think we're going to talk about elastic and inelastic, so we're not going to work with two different equations there, where we're working with momentum and energy, but we are going to work with momentum involving two dimensions, which means we're going to get back into vectors again and adding vectors that unfortunately are not on the same direction. And so I'm going to example 2 right out of the gate because, well, example 1 and example 2 are the same thing, only example 2 is a little harder. And we have worked with these type of skills before, as I mentioned, when we dealt with combining velocities or combining forces. We've done this type of thing. This time we're combining momentum. So here we go. Example 2, a 4-kilogram bowling ball is moving east at an unknown velocity when it collides with a 6.1 kilogram frozen cantaloupe at rest. After the collision, the bowling ball is traveling at 2.8 meters per second, 32 degrees north of east, and the cantaloupe is traveling at a velocity of 1.5 meters per second, 41 degrees south of east. What was the initial velocity of the bowling ball? All right, so as I mentioned, well, it's right in the title here, conservation of momentum. So we are going to be looking at the momentum before is equal to the momentum afterwards. Rho is equal to rho prime. All right, now again, getting back into writing down some of our variables here, we have 2 masses. All right, so our first one I'm going to say is our bowling ball. So that's 4 kilograms. All right, we want to know the initial velocity of that bowling ball. That's what the question's asking here. Now it says after the collision, or sorry, the cantaloupe that it hits, we'll put in there is 6.1 kilograms. There's our second object. Well, it's not moving initially. That's why it gets hit. And so V2 is just 0. All right, but we do know what happens after the collision because the bowling ball, V1 here, or so I'm going to have V1 prime, is equal to 2.8 meters per second. Again, 2 dimensions. So here we go. 32 degrees north of east. Okay. V2 prime. So that is the velocity of our cantaloupe after it gets hit. It's going 1.5 meters per second, and its designation here is 41 degrees south of east. Okay. So there we go. So there's all our information that is given in the question. What we're looking at here is what is the initial velocity of that bowling ball, which means we're going to have direction also here. Now, again, like I said, conservation of momentum. And so we're going to have M1 times V1 plus M2 plus V2. That's going to be our initial momentum here. So what? We got M1, which is 4. All right, times V1. That's what we're trying to figure out here. Plus, now again, the momentum of the cantaloupe initially, it's not moving, so it doesn't have any. 0 plus. Whoops, not plus. That is all the momentum we have. It's the 2 objects. Now, afterwards, we have again M1 times V1 prime and then M2 plus V2 prime. So here we go. We have M1, which is 4, times V1, which is 2.8 meters per second. I'm going to write it really small because we don't really need it. 32 degrees north of east. All right, there's the first momentum afterwards of the object afterwards. Now the second momentum after the collision. So we're gonna have a plus 6.1 times, we got 1.5 meters per second, and the direction here is 41 degrees south of east. All right, now I'm going to simplify this a little bit. Because over here I have a 4 times V1 equals, so I didn't do anything crazy there, Now with vectors here, I can multiply vectors by a scalar. So 4 times 2.8. What do we get there? 4 times 2.8, the direction ain't going to change. 11.2. I'm going to leave the units out. So, yeah, let's leave the units out. I just want room here. But it is momentum units. 32 degrees north of east. All right, plus, now I'm going to go over there. I got my mass times the magnitude of my velocity. So 6.1 times the 1.5. And let's see on the calculator here, I get 9.15. And again, I'm just going to leave the units out here. Let's put a little blank because I know in the end I'll have my units. So I got 41 degrees south of east. Okay, so here's where we're at. I can add these two vectors together. Now again, because it's 2 dimensions, I got to do trigonometry. So which means I got to take this vector, find its horizontal vertical components, take this vector, find its horizontal vertical components, combine their verticals, combine their horizontals, use some trigonometry and the old Pythagorean theorem there to come up with a resultant velocity of putting these two guys together. All right, so here we go. Like I said, a little bit of review. So I'll look at my first vector here. Let's label things here. There's number 1. And we'll call, well, I'll use a different color. There's number 1 there. So 32 degrees north of east. All right, so I'm going to go over here for number 1. Again, compass rose, never enter stinky washrooms. 32 degrees towards the north from the east. Towards the north from the east. So there's our 32-degree angle right there. And it has a magnitude of 11.2. All right, so I need to find both my horizontal and vertical components. So my horizontal here is this way. And my vertical is that way. And since this is number 1, I'm going to call this vector 1. Well, we already got velocities as vectors. I don't want to mess up the notation here. So you know what? I'm just going to call this H1. Horizontal of number 1. And I'll call this V1 again for vertical. All right, notation. I'm going to call that V1. It's not... yeah, anyways, all right. So again, for notation, what's the best way to call that? Here, I got to use different notation here. I don't want to get our V's in mixed up. You know what? We're dealing with momentum. So I'm going to call this...
Mr. Gates, you can use X and Y.
X and Y. You know what? I'm going to stick with, how's this? I'm going to go with rho 1H, rho 1V. Oops, V. All right, so there's the horizontal momentum of the first vector. Here's the vertical vertical component of our first momentum. All right, there we go. All right, a little bit of trick. So again, our hypotenuse is 11.2. And so let's see, I'm going to find rho 1 first, the horizontal component. It is adjacent to it, so it's going to be cosine. So I'm going to take rho 1H is equal to, I take the hypotenuse, short form it a little bit here. And again, it's the adjacent, so it's going to be cos 32 degrees. And rho 1H, let's see, I take cos 32, I times it by 11.2, and I get, 9.5. And I look at my diagram here, it's headed east. All right, I'm going to do the same thing for the vertical component of our first momentum. So I'm looking at rho 1V. Again, it's going to be 11.2. It is the opposite, so it's going to be sine 32 degrees. And my rho 1V, let's see here. Well, put a vector symbol on it because I do know it's going north. And let's see here. I take sine 32 times it by 11.2. I get 5.94. And again, I look at my diagram. It's headed north. Okay. There's one vector down. Now we'll go up here to number 2. Let's go after it. All right. So this is number 2 here, our second momentum that we're going to add up. All right, so there's number 2 here. Sure, have enough room. And what are we in? We're in the southeast quadrant. Okay. So never enter stinky washrooms. We're in here somewhere. All right, 41 degrees towards the south from the east. So there's our 41 right in there. There's our 41. This has a magnitude of 9.15. All right, now this is my second momentum. So again, I'll call this rho 2h, and the vertical component will be rho 2v. All right, so again, use a little bit of trigonometry here. Let's get the horizontal one first because I want to line them up here so I know what I'm doing. All right, so let's see here. So rho 2h, again, our hypotenuse is 9.15. It is the cosine again because it's the adjacent, so we're going to go cos 41 degrees. All right, again, I'm checking out what I got here. Let's see, cos 41 times 9.15, getting 6.91. Check out my diagram. Yeah, it's headed east. Okay. All right, now let's go for the vertical. So rho 2v, again, it's going to be 9.15. That's our horizontal, or our hypotenuse. The vertical component is the opposite, so I'm going to use sine 41. All right, and so rho 2v with a vector symbol on there. Let's see, sine 41 times 9.15. What do I get here? Sine 41 times 9.15. And I get 6, right on. Okay, and again, the direction here, oh, this one's moving south. All right, now, I've got my components of the horizontal components and the vertical components. So now I can combine them so that I can add these vectors together. Now look at this. I get 2 east here on the horizontal. So my rho r for the resultant, all right, horizontally, let's throw an h in there, add 9.5 plus 6.1, and or 6.91, and I get 16.41, and the direction is east. Now I add up the verticals on my resultants. So this time we got 1 north, 1 south. South is bigger, so I'm going to go south here. Ooh, it's a really small number too. That's only just 0.06. And again, south is the bigger one, so south. Okay. So now I can combine them because I know my vertical and horizontal components of my resultant. So let's do that over here. There it is. Never enter stinky washrooms. Again, this will not be to scale because this 0.06 is going to be hard to write. But here we go. So there we go. Horizontally, we're going 16.41. Then we're going down 0.06. Again, not drawn to scale. And this is our resultant momentum right there. And we're going to have to find this angle. Okay, so a little Pythagorean theorem. Now, I'm going to erase some of this because I need some room here. All right, so I'm going to erase this. We don't need those components anymore because we have our resultant. All right, so don't need these components anymore. Use them. Use those though. All right, so as I did before, when we're combining, first I'm going to use the Pythagorean theorem to find my hypotenuse. All right, so that means that my rho r squared is equal to, I take the 16.41, square it, plus this small 0.06, square it. All right, we add those up, and then we take the square root. Let's see here. to 2 decimal places. So clear. 16.41. Square it. All right, plus 0.06 squared. All right, then we square root it. Oops. Oh, in this case, not much going on there. It's 16.41 because I rounded to 2 decimal places. All right, so there's our magnitude. Again, I want the angle now, so I'm going to use trigonometry. So I have tan theta is equal to, let's see, the opposite, 0.06. The adjacent is our 16.41. And I'm getting theta to be, let's see here, 0.06 divided by 16.41. All right, little tan inverse. Oh, 0.21 degrees. Not a whole lot. All right, and that is south of east. All right, so here's what we're looking at now, is that I can now put these two vectors together and back into our equation. So we have 4 times v1, but now I've added those two vectors up where the magnitude is 16.41. All right, our direction, very small. I'm going to have to change this example on that note. 0.21 degrees south of east. So this person's a little bit off. I want to get V1 right, so I'm going to finally divide both sides by 4. And so the initial velocity of our bowling ball, a little bit offline it looks like, because let's see, take 16.41 divided by 4. I get 4.1. Again, now I'm going to throw some units in here because I know my velocity. We're in standard units. It's just meters per second. And it looks like they're a little bit offline at 0.21 degrees south of east. And there we go. So again, we're doing the same skills that we did before when we dealt with velocity and forces. This time we're just dealing with momentum. But as usual, when we're adding two vectors together, finding both their horizontal and vertical components, combining them, and then using them to find the resultant, both the magnitude and the direction of it, to come up with a resultant vector, which then we needed to actually, in the end, had to, again, divide by 4, just because that's what the first mass was. All right, so that is the end of collisions and momentum.